Hi, welcome all. This is a TCS seminar at the Jagiellonian University. Today we're happy to have Marcin Briański, our local student. We tried to establish what was the year that you appeared at the Jagiellonian, and it's fuzzy. 2014. So this all education takes some time, as you can see. Marcin is about to finish his PhD, and today he's going to speak about some unrelated stuff. He participated in millions of projects, very nice results in various subgroups. I'm happy to see together with you another one of them. Please, Marcin.
Thank you. Okay, so hi all. So this will be a structural theory talk, and I think that every structural graph theory talk is incomplete without at least a mention of tree width. So the jump-off point I want to talk to you about is tree width. So it was introduced by many people independently, in mid-70s by Hallin, but for example, the most important work concerning tree width was done in the 80s by Robertson and Seymour. And while it has many important connections to fixed parameter tractability, even logic with things like Courcell's theorem, this is a structural graph theory talk. So for us, the most important aspect of this parameter is its use and theorems related to it in structural graph theory. In particular, I think that that the theorem that captures this parameter in the most succinct way is the grid theorem. So I have written down here that this is from 1986 by Robertson and Seymour, grid theorem. Which I will state in two parts. The first part is that if tree width of a graph exceeds some function of k, then there is a k wall minor in our graph. And the second part is that if there is some sufficiently big wall as a minor, then the tree width of our graph is also large. Right? So, in essence, this tells us that tree width of some graph family is really tied to excluding some wall as a minor. And I'm stating this theorem in terms of walls and not grids, as is usually done, because for what comes, it is actually walls that are important and the distinction is significant. Okay. So, for another part of historical background, in 2014, Wollan introduced and proved a similar grid theorem for immersions. So I will call it the immersion grid theorem. And again, it comes in two parts. The first part is if this time tree cut width of our graph is larger than some function of k, and this function is these functions are unrelated, completely unrelated, at least for the statements I want to give. If this parameter is large enough for our graph, then k wall appears as an immersion in our graph. And dually, if sufficiently large wall immerses in G, then the tree cut width of our graph is at least k. So don't worry if you don't know what an immersion is. I will introduce it in just a bit. And okay, so this is the first ingredient of motivation for this talk, is this immersion grid theorem. The second ingredient is the directed part. So a bit simultaneously, also in 2014, Kawarabayashi and Kreutzer proved the directed equivalent of the grid theorem. So we'll call it directed grid theorem. Yes. And again, same statement. Either if the directed tree width of our graph is large enough, at least some function of k, then a k wall, k cylindrical wall, appears as a minor of our digraph G. And the second part is that if I have a G of k cylindrical wall, then directed tree of that graph, the digraph, is also at least k. So a question that maybe not jumps out to everyone in light of these two theorems: is there a way to have a directed immersion grid theorem? And this is the core of what I want to talk to you about today. So we call it our work. And I will begin with a very predictable statement at this point. Theorem to appear by myself, Mike Hatzel, Karolina Krasa, and Michał Piliczuk, which states the following. There is this directed tree cut width parameter, so abbreviated to dtcw. And if directed tree cut width of some digraph is large enough, then we have a k cylindrical wall immersion. And second part, if I see a g of k cylindrical wall immersion in my digraph G, then its directed tree cut width is at least k. All right. So you can see that it sort of combines, translates this tree cut width parameter to the directed world. It's supposed to be its analog, and what we believe to be this crucial property, capturing graphs without immersions of walls, is preserved. Okay. So to explain to you the content of this theorem, I need to tell you what is a cylindrical wall and what is an immersion. So let me maybe start with walls. So as I said, these are called grid theorems because usually they are stated in terms of having grids as minors and not walls. Well, so grid is the most basic I would say, two-dimensional graph, namely this one. And to get from that a wall is essentially the same, but with degree bounded by 3. So this is the picture to have in mind. And if at any point something is unclear, don't be afraid to interrupt me. I'll do my best to answer any questions. Oh. Now there are many plausible ways to extend this to the directed settings, but the one that was done by Kawarabayashi and Kreutzer in their directed grid theorem is with so-called cylindrical grids and then cylindrical walls. So a cylindrical grid starts with a collection of, let's say, of order k, k vertex-disjoint directed cycles. And then adds 2 k paths, one going from top to bottom, going top to bottom and bottom up alternatingly. So this would be cylindrical grid. Directed. I don't understand the question.
What are these directed?
So this is a directed graph. So E consisting of k pairwise vertex disjoint directed cycles.
Okay.
And
directed cylindrical grid.
Yeah, you can, let's call it directed cylindrical grid. And each intersection point is a vertex of this digraph.
How can you make a wall out of it?
Okay, so it's slightly less straightforward, but this is essentially done by vertex splitting. So this is a general operation that if I have a digraph and I have a vertex that has some number of incoming arcs and some number of outgoing arcs, I can replace it by a pair of vertices connected by an edge and one collecting all in arcs and the other collecting all out arcs. In applying this operation to every vertex of a cylindrical grid, we obtain a cylindrical wall. And to make it more concrete, I can draw to you how it looks like. So again, we'll have this k vertex disjoint cycles as the base of our structure. And now we'll have, again, paths going up and down alternatingly, but each time intersecting in an edge with the cycles. So going down like this. And here I'm just highlighting that there are no two edges. There's just one edge, and it's also part of this path. Yes. And again, we have k paths going up and down. So this is the object of our interest. So that's the first ingredient of understanding the statement of this theorem. The second.
What happened there on the bottom? How many vertices are there between
How
red
many?
and the green, or I don't see?
Here, there are no vertices here.
No.
So this is just a very long edge. It's long because I needed space to draw the paths. Yes.
It matters the order in which you select the vertices and do the splittings, or
No.
to some ramps you recover the same.
It completely doesn't matter. You don't need Ramsey or anything. You can just apply this operation globally. That's more how I imagine it. So you introduce 2 vertices per each vertex of the old digraph, and called in one called out, and you connect them as you see in that picture. Okay. So the second part I need to tell you to understand at least part of the statement of this theorem is an immersion. So I will start by telling you what is an immersion in the undirected setting. So I have 2 graphs, H and G, an immersion model of H and G is a map, let's call it mu, with the following properties. So mi of V, where V is a vertex of the guest graph, are pairwise disjoint branch vertices. Pairwise distinct vertices of G, and mu of U V, where this is an edge of our graph H, is a path from mu of U to mu of V in G. And moreover, these paths taken as a whole are pairwise edge disjoint. Yes. And in a sense, it's perhaps easier to think of it as a generalization, or taking the notion of a topological minor and replacing vertex disjoint with edge disjoint. In a topological minor, we would have the same map mi, but each time it will be a path it will be family of paths that are internally vertex disjoint, and we replace this notion by edge disjointness. Okay. So maybe let me try to draw a quick example. So this will be my graph, and I will try to immerse somewhere. This is H. And this will be G. So first I need to select 4 vertices in G. Cannot coincide. And now I need to root each edge as a path in G in a way that I cannot reuse edges. So for example, maybe I root this edge like this, and maybe I root this edge like this. And then I need, say, an edge here. So these would be these 2 edges. And all that is missing is this connection, and maybe it goes here. And of course, these paths can be intersecting at vertices. That's completely legal, but they cannot reuse edges. Okay. So this is the undirected notion of an immersion, but it is very clear, I think, how to translate it to directed graphs. Yes? If this edge in my host graph in my guest graph has a direction, all I need to change is to require the path to be a directed path with appropriate start and end. Yes?
Do you allow multi-edges or multi-arcs?
Yes, I allow multi-edges. But here, I each time I was drawing these arcs, I imagined this to be a path. So there could be multiple edges, multiple vertices on the way. Okay. And from this, we can glean some observations. Well, for example, if H is a topological minor of G, then H is also an immersion in G. Yes? Because if I have a family of pairwise internally vertex-disjoint paths, then they are in particular edge-disjoint. This is nothing too complicated, but there is this is substantially different notion than a topological minor. So let me give you an example. So consider the following graph. So I take a center vertex and a collection of let's call them peripheral vertices, and I just collect them by 3 arcs. So this is a graph of very low tree width. Like after removal of one vertex, or multigraph with low tree width. After removal of one vertex, you're left with an independent set. There is, from the point of minors or tree width, this is completely uninteresting. However, one observation can be made that if the maximum degree of H is at most 3, then H immerses in this triple star for large enough K. K is the number of those peripheral vertices here, at least the size of the number of vertices of H. And it's clear how to do it. I just map vertices of H to the peripheral vertices here, and whenever I want to make a connection, I make it through the central vertex. And in either case, because the maximum degree is 3, I will not run out of space to do it. So there is something very similar, a very similar object in the directed setting, but it's slightly more complicated. So what turns out to be the directed equivalent of this object is something called an onion star. Okay. So what is an onion star? We again have a central vertex through which we'll be routing every edge of our target digraph, and some number of peripheral vertices. But this time, there are 2 types of vertices, of those peripheral vertices. We color them red and green. Some are in vertices, and the other are out vertices. And the point is that there are 2 arcs towards the center from an in vertex and one arc back. And 2 arcs from center to this peripheral vertex and 1 arc back for the out vertices. Okay. And here the conclusion is weaker than in the undirected world, because as you can see, what we'll pack will have are vertices of total degree 3, at most 3, but each vertex has either 1 outgoing edge or 1 incoming edge. Okay. But what is relevant for us is that this is property that cylindrical wall has. Every vertex has total degree 3 and either one outgoing edge, like this vertex here has just this outgoing edge, or exactly 1 incoming edge, like this vertex here. So cylindrical walls immerse in onion stars. So somehow,
This means that it doesn't make sense.
No, this just means that from the point of asking what you can root edge disjointly, the answer is almost everything here.
Yes.
And the same conclusion is for that animal there. Okay. So I'm not going to define tree cut width or how it works, although I think that the proof from the Wollan's paper is really, really nice. But sort of an intuition one might have from this example is that free cuts, so cuts by free edges, are much more dangerous to what you can immerse than two cuts or one cuts. Because one cuts are kind of useless. Two cuts became like an edge because you can almost go and then come back. But free cuts enable some sort of branching. So you need to really control how it behaves, and you can really see it in the definition of tree cut width. And well, here we have those two kinds of nodes, but at the same time, if I just had just one kind of nodes, like I had a almost onion star, but I have just a bunch of those oh, I think I reversed those things. Bunch of those out onions hanging here. Then this doesn't immerse a cylindrical wall. Like I cannot pack half of the vertices. I have no space for them because those guys don't work. And the same conclusion will be true if I have just, say, two guys that are in onions. This still does not immerse a wall. So we need to be able to decompose these guys, but not these guys. Okay. So at this point, I would like to tell you what is a directed tree cut with decomposition. So I have a digraph, let's call it G. So I have a digraph G. A directed tree cut with decomposition of G is the following quadruple. So there will be a tree, there will be a near partition function, some edge guard function, and some node guard function. Okay. So what is happening? So T, as you can guess, is a tree. Beta is a near partition. So it's a map from vertices of our tree to subsets of vertices of our digraph. And what does it mean that it's a near partition? Well, it just means that every vertex appears somewhere. And no vertex appears in two places. And it's a near partition because some bags might be empty. So it's not quite a partition. Okay, so what is gamma? Gamma maps every edge of our tree to some subsets of the edges of our digraph. And theta maps nodes of our tree to some subset of the edges of our digraph. So obviously there are some conditions on those edge sets, and I will try to tell you what they look like. So let us first look at gamma. I call this the edge guard set. So I have my tree, and I have edge in this tree. So because I have this near partition beta here, this edge cuts the nodes of my tree into two sets. So via beta, this introduces a cut in my digraph G. So this is a cut. So what is property of gamma V? So this is a heating set for all cycles that contain a vertex of A and of B. So in my digraph, I see a cycle that goes somewhere like this. So one of those edges must belong to gamma. Okay. Is this part clear so far? So this is heating set for cycles crossing cuts shown by T.
So in particular, if I had only edges from A to B, this could be empty.
Yes, if it's actual directed cut, so there are edges just going in one direction, there are no such cycles, so the empty set works. But in general, this could be some more complex set, and it can contain edges anywhere in the digraph, not just in the cut. Okay. So story for theta is more inspired by these onion star examples. So what is different if I have because now I'm mapping from nodes to sets of edges, and you might guess that this is a heating set for something, and it will be heating set for some kind of onion. So now when I have this selected node T, I again see some possibly big number of edges incident to T. And each such edge, again, introduces a cut in my digraph. But now I have a selected side I care about. This side containing these nodes. So let me call this side B always. So this is now an ordered cut. And this is supposed to be, for each node, an edge heating set for all out onions or all in onions. Yes. So what is an onion? Well, I told you what onion star is, but not really what is just an onion.
But you should relate it to A or B. Right?
Yes, and this is this in-out.
Oh, wow.
So an onion is a digraph with two nodes. Let me call it the tail and the head. And there are two arcs from the tail to the head and one arc back. And now when I see a cut AB, so I have a side A, side B, and remember, once I selected node B, this side is predetermined for each cut. In onion will be one where T lies in T. It's an immersion model of this digraph where vertex T is in A and the vertex H is in B. So I need to hit all of those, or I need to hit the reverse side. So the vertex H being here and the vertex T being here.
So this is when tail is in A.
Sorry?
So in onion is when tail is in A.
Yes, so in onion sends two arcs towards my side, and out onion sends two arcs from my side, and one arc in the other direction. Yes?
So this is saying for each node, you want to hit all out onions or all in onions, so
yes.
The choice is independently made for each node.
Yes. So again, an intuition can be gained here. So how to decompose this guy? Well, I have a central bag with just the center vertex, and each other leaf vertex lives in its own bag. Here, as my heating set, I take, say, all these edges I see here, for the center guy. Other guys have empty heating sets. And I see that I will only ever see an out onion. I will never see an in onion. Yes. And here it's quite easy to argue that this doesn't have a decomposition with everything bounded.
Why do you take all edges of each?
Yeah, you can take just one. That will also. Yeah. Okay. So to continue, to finish, I need to tell you what the width of a decomposition is, and this is really quite straightforward. Width of some decomposition T is just the largest, and here I take size of a bag, size of an edge guard set, or size of a node guard set over all T vertex of my tree and all E edge of my tree. So if you can decompose a graph with bounded size bags in the near partition, bounded size cycle heating set for edges of your tree, and bounded size node guard sets for those out or in onions at each node, you have a decomposition. So it's a quite complex definition, but
so is it your definition or?
Yes, yes, we came up with this definition.
Okay, so it seems like tricky to start talking. What does it mean that this width is large? Like no idea. You need some dual object or something. Do you have a dual object for this?
Yeah, the cylindrical wall.
Oh, well, but you need to. How do you? How do you prove the first implication is logical? Yeah.
First one. So going from large directed tree cut width to.
Yeah.
Okay. That's the side I will try to explain today.
Yeah.
Yes.
You have a simple example why the width could be large, but just because of this gamma E and not because of the rest? Or it's hard to explain?
Yeah, I think if you just take so this, if you allow multi-graphs, then it's easy. Just have two like a lot of nodes that have pairwise many arcs in either direction. Yes. Then you have at least two bags, and between them you will see large flow in either direction. So large number of pairwise edge disjoint cycles. So the edge heating set must be large. Does that satisfy you?
But then it's kind of clear that you would have a large cylindrical wall if you have lots of these edges forth and back between two vertices?
Between two vertices, no. But if you have a lot of them, then yes. This is
why the width of this two vertex graph with many edges forth and back?
No. I said many vertices.
Many. Oh, sorry.
Yeah, if there's just two of them, then yeah, this has small width because you can just put them in the back together.
Yeah,
then you
exactly.
don't need to do anything.
Yes.
Okay. So, so the part I will not devote a lot of work to, a lot of space during this talk because there isn't enough time, is the second implication. But while this is a bit tricky, it's not so bad. And mainly because this parameter has maybe not immediately obvious, but a nice property that if I have if H, a digraph, is an immersion of digraph G, then the directed tree cut width of H is at most the directed tree cut width of G. So it is immersion monotone. And this is a fairly straightforward translation. If you take a decomposition of G and an immersion model of H, this exactly tells you how to treat it as a decomposition of H. Okay. So this simplifies the second part that you just need to take a wall and argue that it has a large directed tree cut width.
So is it obvious that it has?
No. I mean, it's definitely not obvious. It's much simpler than the other part. But so I will, and I think it's the other part is the more interesting part.
Yeah, so you don't have any notion of a bundle or something like this.
No.
The proof I know in the usual setup was through bundle here, right?
Yeah, for the grid theorem.
Yeah, I take the family of crosses and then I argue that.
Yes, we don't have such a nice proof.
Okay.
In particular, it's not so tight. I think we take a grid of order k squared to argue that it has a directed tricut with k.
Okay.
But this is also the case in undirected tricut with. There isn't such a strict cutoff for the walls there. Okay. So there is a schema we follow in the proof of this property one. So what is this schema? So we start with some rough decomposition. Of so the setup is we argue that if G has no K cylindrical wall immersion, I will show you a decomposition of bounded everything. Yes. So in this step, we call this the potato decomposition. The idea is kind of to guarantee everything except for this status. So I will explain exactly what I mean a bit later. But this turns out to be this was we had for close to a year an idea what this rough decomposition should look like, and we just struggled to prove this theorem. So once we have this rough decomposition, we'll define a suitable notion of a torso. Yes. So a torso is supposed to have this decomposition almost kind of what you want, and you locally encode information how this interacts across the rough decomposition. Then decompose each torso. So we will argue that if the torso has a large wall immersion, and the original digraph had a large wall immersion, and the nice property of our torsos will have is that they will have a bounded number of vertices of large degree, meaning that after deletion of not too many vertices, each degree will be bounded, and then we'll just apply directed grid theorem. Yes? If we have no cylindrical wall immersion, there is no cylindrical wall minor. So we can apply the directed version of grid theorem, get the directed tree of decomposition, and because, okay, I have not defined to you what directed tree of is, but the way to think about it is that you have sort of a decomposition where instead of arc hitting set, you have vertex hitting sets. But if I have bounded degree, I can translate the vertex hitting set to an edge hitting set. So by this clever application of directed grid theorem, we'll get the composition of a torso, and then assemble torso decompositions into global ones. Okay. So I need first to tell you what is this rough decomposition we start with. So it will be potato decomposition. So here we'll have, again, a tree, but this time it is rooted. A new partition function beta, and an edge guard function gamma. So gamma is essentially the same property as the one required here. It's an edge hitting set for cycles crossing the cut shown by this edge. So gamma as before. But now there is this extra property. So the first one is that if I have xy in beta of t, x different from y, there is large flow. Yes. So this, what I require of this decomposition is that if I left two nodes in the same bag, the only reason I can allow myself to do that is because I see pairwise flows between those vertices. Yes. So if I replace the notion of x and y, I get a large flow backwards. And the second property is that when I look at the node, T in my tree, so there is a parent edge, and I see some subgraph here induced by the subtree. If T is different from the root, then this must be strongly. And a lemma we took so long to establish is that every digraph has a potato decomposition of this kind with gamma bounded. So for this particular step, we don't even need the assumption that there is no wall immersion. We need a wall immersion argument to argue that each bag has bounded size. But for now...
Sorry, can you repeat the definition I just zoomed out for a moment? So you have a tree rooted.
Yes.
Beta and gamma. Beta is for the partition of the vertices of G. Gamma is more or less the same.
It's exactly the same. It is a hitting set for the cycles that cross this cut.
And the properties you list there are what?
The first property is that if I see two vertices in the same bag, the reason is that there is a large flow between them in the digraph.
Flow?
Yes.
So the family of edge-disjoint paths?
Yes.
Between two subsets?
Between x and y.
X and y.
Those are vertices.
Two vertices, then there is a flow between them.
Yes. So if I have two vertices with a small cut between them, they are in different bags.
So what does it mean large then?
Well, at least K.
What is K?
The quality of this potato decomposition.
Okay.
This is a K potato decomposition. If this has...
so if they are in the same partition block, then there must be a K flow between them, okay?
Yes.
And the second?
The second is if I have a vertex that is not the root, and I look at the subtree rooted at this vertex, this gives me a subset of vertices. This must be strongly connected. Strongly connected just induces a strongly connected subdigraph in G. Yes, so if there are two, there cannot be a cut of order 0 in here. So there needs to be just flow of size at least 1 in each subtree.
And then you say that every graph has this property
with size of gamma of E at most some function of K.
Function of K.
Yes. If I require flow K, then the size of gamma of E will be function of K.
So this is suspicious that it's for every graph then.
But I allow you bags that are super big.
So like everything in one bag? Or?
Well, no. What holds you is the condition 1.
Yeah, yeah.
But at this stage, bags can be big. So there is a separate argument that if you have a too big of a bag, we will find you the wall immersion. So if you have no wall immersion, you have this potato decomposition. But, well, onion star has this decomposition as well. So this is not good enough yet. Okay. So I need to erase something. Let it be this. So I'll try to tell you what a torso is.
So is it the proof idea that you start with everything in one block, and if there is a there is no big flow between the vertices, then you consider the cut and you split the. Is it the idea at least?
Yeah, kind of like this. The point is slightly more complicated. So you start with this tree. So for k equal 1, you just require that each bug is strongly connected.
Yes.
Kind of. So you can start with decomposing it into strong components and taking any tree. And then once you have the composition of quality k minus 1, you look at this flow connected set and you consider all k cuts on this set. So there are no cuts of lower order, but there are k cuts. The point is that you can uncross those cuts on this smaller set. So it is not true that you have a global uncrossing, because die cuts do not uncross as well as unordered cuts. But cuts of minimum order do uncross. And they uncross just on this set. And then you know that a laminar, so this is a laminar family just on this set. So you can replace it by a tree there. And there is a bit of work to clean the situation out, but this essentially works.
Nice.
Okay, so now we have this potato decomposition of our digraph. So I have a bug. So this is beta of t. And there is some number of vertices here. And there is some number of subtrees that hang in my decomposition. So I want to represent this entire subtree by just two vertices. There will be a vertex collecting all in edges and a vertex collecting all out edges. Yes? So if I had an edge like this, I will replace it by an edge like this. So this was an edge in G, this will be an edge in the torso. Yes? And similarly, if I had an edge like this, I will replace it by an edge like this. So this is in, out. And well, since this is strongly connected, it makes sense to represent it by a cycle. But this turns out to be not quite good enough. So I will just represent it by this. So it's a very, very tiny onion in there. So I call this the Chekhov edges.
So it's an arbitrary choice if the two edges go from out in or not?
No, I want those edges going from out to in, because if I have two edges from in to out, then it's possible to route two things through this component, and previously it might have been impossible. Yes? Because I could route two edges to in, two edges to out, and somewhere here. And maybe there's just one edge you can route there in the original digraph. So this is this choice is better because it doesn't enable you to route new things that were previously impossible. And this is captured by the property, the lemma. So if 2k wall immerses in the torso, then a k wall immerses in the original digraph.
So torso is this bar beta plus these two
plus two vertices per each child.
And you drop the vertices that are outside.
Yes.
We should believe that someone.
So the idea is that for you roughly lose half because it might be impossible to route both in and out vertex in a single component. But you can always route at least one.
Okay.
And when you are routing just an edge for a component, you can do this by strong connectivity assumption over there. So this is a slightly more complicated than that, actually, but it is not too hard to prove this. And here it is important that those are actually two arcs in that direction and not the other way around. But in this direction, they are safe.
from your assumption, you don't have a large wall in the torso.
Yes, exactly. And now the second observation you can make is that in vertex has exactly one outgoing edge, out vertex has exactly one incoming edge. So all those vertices have small degree. So the only vertices of high degree are here. And as I said to you before, the idea is now to apply.
So your degree is the minimum of the two?
Yes, let's say that.
Okay.
So the degree of a vertex is the smaller of in degree or out degree of a vertex. Yes. And so how can I decompose a torso? That's the next step in my story. So the idea is that I have this set that's not too big of vertices of large degree. So now we apply the Erdős-Pósa property for triangles. Yes. So this is previous work done in this project, and it says essentially that onions with fixed tip have an Erdős-Pósa property. So either I have a large edge-disjoint packing of them, or I have a small edge heating set for them. So there are three cases. I have a heating set for out onions. I have a heating set for in onions, or packing of both. So the idea is that if I have a packing of both, and I have a pairwise large flow between those vertices, then I can construct from that an onion star.
So this packing of
out onions and in onions.
So this packing is in the torso, right?
It is in the torso. Yes. So there is a similar lemma here, but actually here loss is 0. So if you have an onion star in the torso, you'll find it in the original diagram.
Yes. Oh, really? Okay.
Yeah.
Okay, so these onions are in this graph induced by the beta.
So the center of the onion star is in here, in this beta,
okay.
But the petals can be in these components.
Okay.
So.
And then you say that if you have a lot of these onions plus this large connectivity flow, then this will give you a wall.
Well, it will give me an onion star even, and from onion star I will get a wall. Yes.
Wait. Aha, because onions were these small guys, these two vertices.
Yes.
And the star was
a common center, and from this center, k out onions and k in onions that are pairwise disjoint, except for the center.
I believe you. So this should be easy, probably.
It's not.
It's not easy.
It's not that easy. So
because these connections between the petals, they can interrupt your petals.
Yes.
And that's a problem, probably.
Yes. So what happens? So I wanted to skip it a bit because this is a bit out of topic. But there is an example where you take a grid, you orient everything from top left to bottom right, and here dually like this. And now take two vertices, X, Y, and you orient edges like this. And like this. So, and apply split here. So I will not draw how it looks like, but the
split. Okay. Where do you apply?
On every vertex of this white grid. So the point is that there is a huge flow from X to Y and a huge flow from Y to X.
Wait, where's the flow? X goes here.
and repeat.
Okay, okay.
And the same for y, just symmetrically.
Okay.
But every such path, every x to y path, no matter how you route it, will intersect every y path, y to x path. This is Heck's lemma. Yeah?
Okay.
Yeah, so they intersect in a vertex. Yeah. So after split, they intersect in an edge.
Okay.
So that means that there is a huge flow in both directions, but there is no simultaneous flow there and back. So there is no cycle that contains x and y. Because once I remove an x to y path, I have cut away y from x. There is
that should be a problem for your statement. No?
So this is rescued by something called onion harvesting lemma.
Oh, wow.
And it essentially states that if this situation occurs, you have an onion star.
Onion star. Yes.
And this is work of Łukasz Bożyk, Oskar Defrain, Karina Okrasa, and Michał Pilipczuk.
So where is it here? Where is this onion star here?
Like here. So you go here, 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 here. Yeah, here. So this is one out onion, and it strips something
so the
here.
two from X, they merge, and then one back to X.
Yes.
Okay.
And and this is an in onion. And one strips something from leftmost side, and the other from the rightmost side. So I can pack a lot of those and a lot of those.
So the packing you wanted edge-disjoint, yeah?
Yes, edge-disjoint.
Okay, edge-disjoint. Wow.
So this will be an onion star with center X. But I wanted to avoid stating this lemma, but it is actually...
this onion harvesting lemma is published?
Yes. And this is like, I don't know, 12 or something pages of the proof.
Really?
Yes. So this is complex, and actually this is, I think, the only place where we have a non-elementary dependence in our proof. So our proof is non-elementary bounds, and this is the source.
By non-elementary means
iterated.
The function is not explicit.
That the function is not some combination of, it's not a finite length power tower.
Oh.
Not bounded length power tower. Yes. So I hope this convinces you that if I have a packing of both, I will find my...
So wait, it's an open problem if this onion harvesting lemma is true by some function that you can actually write.
Depending what you mean by right, but yes. If you say elementary function, then I think it's open.
It sounds fun.
You can try to think about it. It would be nice for our result, because then it would be elementary dependence everywhere. So it's not so bad.
It's a beautiful problem then, eh?
No.
You're not too excited about it.
I think that what I would be more excited about is algorithmic application of this parameter. That would be something I would think, oh, that's great.
Give me a reason why you do this.
Yeah, I could then say this is computer science, not graph theory. But back to the idea. So what happens is that so this case gives me onion star. So this cannot happen. So I either have a packing for out, heating set for out, or heating set for in onions. So a natural way to decompose the torso is to put this back here, beta of t, and this heating set for onions gives me what's supposed to be theta of t, this fourth ingredient of our decomposition motion. And now I can keep stripping out from the rest of this digraph a decomposition via the directed.
So these exist their edges, right? So
yes.
Okay.
And here I can extract a decomposition with a bit of a clever trick using the directed grid theorem. So I hope this convinces you that we indeed can decompose each torso.
You decompose each torso. Okay, so this means that
that I have a bounded width directed tree cut with the composition of each torso.
the goal is for the whole graph. You have it for each torso. And torso is defined with in the context of a single.
This potato decomposition. Yes. So now what happens? So I have my potato. So I will go from leaves up in the potato decomposition, and I will decompose the subtree at this stage. Yeah, so this is my potato decomposition. Possibly some edge to parent, and I have a decomposition of each of those guys. And the guys here are represented by two vertices that pack this tiny onion on them. And I have a decomposition of this torso. So I have this decomposition here. So, a priori, those vertices can be in different bags. So I have a vertex here, and a vertex here, and I don't know where I want to connect this decomposition I have here from induction. So, let us do the naive way and say that each out vertex, so this guy, is transferred here.
What? So the picture on the left is what?
This is the potato decomposition,
okay.
And these yellow guys here are directed tree cut with decompositions of those subtrees.
So potato decomposition is like given for a fixed part of the, what is this?
So potato decomposition tells me subsets of vertices per bag, and edge heating sets for each edge for cuts in the digraph induced by this edge.
But this is all in the context of some tree.
Yes, this is all along a rooted tree.
Okay, so you have such a decomposition for each
digraph.
Okay. And the picture on the right is what?
And this is the directed tree cut with the composition of the torso. Yes. So what I want to do is to take this out vertex here, so this out vertex, remove it from this bag, and move it to its in vertex. Okay, so this seems not for free, yes? Yeah, because how many guys can move across this node? So he had this red vertex and this green vertex on different sides. Well, this is where those Chekhov edges come into play. Because I have this tiny onion on them, and those guys, so maybe we draw a schematic picture here. So I have this node T, and somewhere here lives the in vertex, somewhere here lives the out vertex. Then, from the point of view of this cut, this is what? This is an in onion. Did I write it correctly? No. So this is an out onion. Yes. But from the point of view of this cut, this is a different kind of onion. So regardless of the choice made at this node, it needs to be hit. So across this node, I move only bounded number of vertices from left to right because of these magical edges here. So I can fix all hitting sets I see, because if I add those three edges incident to those vertices, their placement plays no role. So I will blow up the width of my decomposition by a factor 3 at most by this move. So now what happens? I have this decomposition. I know that this in and out node, that there is this selected node in this decomposition that contains these two vertices. So I take this corresponding tree cut with decomposition I get from induction, and I attach it here and erase these two nodes. And now I need to finish by telling you what is the guard set for this edge. But this is something taken care of by the potato decomposition. So I have a guard set for this edge, and I use it exactly here. So combining everything, I will end up at the root with a global decomposition of my digraph of bounded width. And yeah, so this trick with useless edges rescues this torso construction at the very end. I was really happy with this trick. It's amazing. Yeah, so that's it. That's all I wanted to tell you today.